Hey all, this is Derek, and this is section 7.2, polynomial inequalities. And this section, so we're looking at polynomials again, just like we did in 7.1, but this time we're going to have greater than or less thans rather than equals to. So we'll expect to get solution sets rather than maybe particular solutions if we're just solving set to 0. And we're going to look at two methods for doing that. We're going to use test points, which are perfectly fine, but they're just not the one that I prefer. So I'll do one example of that. And then I think this is I think polynomials are easier to solve by graphing. So I will show that version. That said, you can use whatever works best for you. And I think rather than going through this big boring box, which I've tried to do a couple of times and I keep cutting it out, I'm just going to go straight into a problem and sort of talk through the methods, and that's going to end up actually covering all this text that I have here. Okay, so first method we're going to look at is using test points. And so the problem with a polynomial with an inequality is that it doesn't quite it's not like you can just solve it over like you can with a linear one and one side works and one side doesn't. This could have infinite little chunks of the number line that will be solutions and infinite other chunks that won't. And we have to have some sort of systematic way to figure out where our solutions are and where they aren't. So test points is one of those systematic ways. No matter what method we're using, like I said earlier, we're going to start by trying to find our zeros. So that's going to involve factoring this. So we're looking for two numbers that multiply to be -10 and add to be 3. So that will be x plus 5 and x minus 2. And for a second here, I'm just going to write equals 0 because I'm going to actually find the zeros first. So that gives us x equals -5 and x equals 2. So those are the two values that if I plug them in here, that would give me, it would make it come out equals 0. So now what these are my boundaries. So if I kind of think of a number line, I'm just going to call this -5 over here, and I'll call this one 2. If I think of this number line, if I put in -5, this will come out 0. If I put in 2, this will come out 0. So it makes sense that it's doing something else in these other three regions, and that's where I'm going to use test points and figure out, was it positive and then 0 and going negative, or was it negative and then 0 and going positive? Or were they both positive or both negative? We don't know. If you think about what the graph of this would look like, you actually do know, and that's going to be our next method is graphing, which is, to me, way easier. But here it is with some test points. So I'm going to plug in x equals -6 into this original equation. So that would give me -6 plus 5 and then -6 minus 2, or -1 times -8, which makes a +8. So what that means is on this region right here, all of these values are going to be positive. If we look back here, that is actually what I want to happen, right? I want all the x's that would make this come out to a positive value because positives are greater than 0. I don't want the equals, so I would not want to include that part. If I test, I'm just going to pick an easy number between -5 and 2, and an easy number would be 0. So if I test that, I'm going to see what it comes out on this interval. So that would be 0 plus 5, 0 minus 2. 5 times -2 would equal -10. So it's negative on this interval. Negative values are not greater than 0, so this is not going to be a solution. And then I'll pick an easy number over here, like x equals 3. And you can see I'm just picking something convenient from each interval. That would be 3 plus 5. And 3 minus 2, oops, not equals 0, 8 times 1, and that equals 8, and so that is positive. So that means all of this is also a solution. And so that's the idea of test points, is we just figure out where our boundaries are, which is at the zeros, and then we grab one point from each interval and we test it, and if it comes out, in this case we're working with greater than 0. So if it comes out positive, then that's a solution. If it comes out negative, not a solution. If this had been reversed and this was less than 0, we would have wanted our answer to be the negative region. And then typically in this, we'll give our answer in interval notation. So this goes from -infinity up through -5, not inclusive, union, to infinity. Okay, so the next step will be graphing. And I have graphs here just to sort of draw on something. That said, you do not need to make a good graph, and you'll see why here in just a second. So for this one, we're going to graph this function. And really what we need to do is get the zeros and figure out, is it above or below? So I don't need to look at this like a parabola and get my perfect, here's my vertex and all that good stuff. I need the zeros because that's going to be where those boundaries are happening. So if I just factor this, I would have x plus 4, x minus 1 should multiply to be negative 4, add to be 3, less than 0. So that is x would equal negative 4 or x would equal 1. So that's my zeros. Negative 4 and 1. This is an x squared, it's positive even. So just treating it like a polynomial, it's going to be positive even, so it will look like x squared because it is x squared, and it will be opening up. And so that's my graph. I want the areas where when I put in x's, they come out less than 0. And where that's going to happen is right in here, where we are below the axis. So here, when I put in these x's, it's positive. When I put in these x's, I get out positive values. But when I put in those x's, I get negative values. So that region right there, that's going to be between these two x values is where I'm going to get less than 0. And since it has a less than, here I'm just graphing the function, right? So, but here I'm actually dealing with the inequality. So I want to be careful to say negative 4 to 1 and not include the endpoints on that. Okay, so for this one, same idea. I'm going to graph it, and then I'm going to kind of figure out, am I looking for above the axis or below? I like inequalities when it goes x and then less than greater than number. So I'm going to bring everything to this side, and that is going to make this a little bit, So I'm going to add that. That's going to be a 4x squared. And I subtract that will make a negative 3x, and that is less than or equal to 0. So from here, I'm going to, there's a couple of things I could do. I could factor, well, I need to factor. So I could factor out a negative x, and I could leave this sign. Or if I don't like the idea of factoring the negative, I could also multiply both sides by negative 1. And that will clean up these signs and make it a little bit easier. When I do this, I have to remember to flip the direction of the inequality. And that means I'll be graphing a little bit different function, but it will have the exact same solutions as if you graph this one. I'm just doing this to make the factoring a little bit easier. Again, you could factor out a negative in front, and we would get the exact same solution at the end with a little bit different pictures. So definitely more than one way to do this one. And minus make a plus 3x. And now that's the part of this method that isn't great, is you do have to remember to flip that sign. Versus when you try to factor out the negative, I find people make a lot of sign errors. So I'm not sure which one would go better. I think that's a lot easier to factor. So that's kind of my argument for doing it this way. Looking at that, I'm going to take an x out, and that's going to be x squared minus 4x plus 3 greater than or equal to 0. And then what multiplies to 3 adds to be negative 4 sounds like x plus, not plus, x minus 1. Ignore the big blob. And then x minus 3. And so my zeros are at x equals 0, x equals 1, and x equals 3. And so for this, I want to have, let's see, here, here, and here. I could have made this come out a little bit farther. Actually, I'm just going to come down here. And so I'm just going to make myself a little bit bigger picture. And this is kind of what I was saying. The scale really doesn't matter because we just need the above and below. So let me blow that up a little bit to make it easier for you guys to see. This one is okay, so notice I just came up here, which was totally wrong. The function I am actually working on is right here. So even though this started as a negative x cubed, because I did that bit with the negative 1, I've now turned it into this one. So I have to be careful and graph the thing I said I was going to. So this is going to pass through there, and then come back and go up from there. And from here, we wanted the greater than, so that means we want these positive regions. So we went from here to here, and then from there to infinity, because that's where the graph is, right? above the axis. So that is from, and these are all equal, yep, so that is from 0 to 1, union 3 to infinity. Okay, so this one is already factored, which actually makes it a bit easier. So this is going to be x equals 0, x equals 4, and x equals negative 3. So there's 0, negative 3, and 4. And then that one is cube, so that's going to cross. That one was squared, so that's going to bounce. That one has a cube, and so that is going to cross. And if I add up our powers, we got 3, 6, 7, 8. So if we FOILed all that mess out, it would have been x to the 8th, so it should kind of look like a x squared. So we're going to come in at negative 3, we're going to cross on that one. At 0, we are going to cross again. Then it's just to bounce off of the 4. So our graph should look something like that. We again want the greater than, so that's going to be the regions above the axis. So all of these x's give me graph above the axis. These ones do not. Those ones do. And these ones do. Here, this has this very sneaky little thing. This is a greater than 0, so it does not include the 0. It does not include the 0. And that right there, that's the one that's really easy to mess up. It doesn't include that 0. So this is going to go from negative infinity up through, where was it, negative 3. And then union 0 to 4, union 4 to infinity. And it's really easy to go 0 to infinity and inadvertently include that one extra 0 that can't be there because it can't equal 0. Okay, so for this one, we got a negative in front. And I got, let's see, 1, 2, 3, 4 x's. So this would be a negative x to the 4th, and so I would expect this to open down. I have x's at 4, and that's even, so that will bounce. At negative 2, that's an odd, so that will cross, and then at negative 5. And again, odd power, so it crosses. Coming over here, we got 4, negative 2, negative 5. And starting from the bottom, so we're going to come in, we are going to cross on negative 5. On negative 2, I'm going to cross again. And then off of the 4, I'm going to bounce. And so again, here's where I'm not worrying about that y-intercept because it'd be 16 times 10. I think it's a negative 160. So this is going to be way off the graph, which is kind of not what we're worried about. This time we're looking for the x values that make this come out less than 0, right? So if I plug in any of these x's, I'm getting these negative values that would be true. They would be less than 0. Here, it would not be true because I get positive values. This one has an equal, so this time I don't have to be careful with that 0. I can just say everything down here is less than or equal to 0, so I can include all that. So that would be from negative infinity up to negative 5. And then bracket union negative 2 to infinity. And again, nothing special about that point now because of the equals. Okay, so then these last few examples are finding domain of root functions, and we weren't able to do this back in the root chapter, at least to this extent, because we didn't have the ability to solve these kind of inequalities. But now we do, so now we can. So as a reminder, to find the domain of a root, at least an even one, we say whatever math is under the radical, we just say that math has to stay greater than or equal to 0. And that's true because if we had with at least a square root or an even root, once I start getting negatives in there, that's complex numbers, and that's not going to be in the domain. So for here, what we need to solve is x cubed minus 25x needs to be greater than or equal to 0. So we factor, get our zeros, and then we can either do test points or graph it, whichever is your preference. So x squared minus 25 greater than or equal to 0. And then x plus 5, x minus 5. And so our zeros are at 0, -5, and 5. So I'll just kind of declare that one to be -5, this one to be 5. And let's see, we had an x cubed, so it's going to come in from the bottom and then do something like that. And we want where this is greater than or equal to 0. So that's going to be this region in here and this region out here. Oh, and this one has these really dumb directions. What is the least value of x in the domain? So we would say the least value of x is right there. It would be x equals -5. If it asked for the domain itself, it'd be -5 to 0 and then 5 to infinity, which is more what the next one does. Okay, so then for this one, find the domain of the function. So this time we're actually finding the domain. So this will go t squared plus 4t minus 5 needs to be greater than or equal to 0. And so this will be multiplies to -5, adds to be 4, be t plus 4 and t minus 1 greater than or equal to 0. And so if you think about kind of what that would look like graphically, this is t equals -5, t equals 1. It would just be kind of a parabola opening up, and this would be -5, and this would be 1. So the places this is going to be greater than 0 would be at those edges. So my domain is going to be from -infinity up to -5, bracket, because square root of 0 is okay, it's just 0, and then union that with 1 to infinity. And then our last one here is domain for this. If we think about where t squared plus 4, where is this greater than or equal to 0? Well, t squared plus 4, think of x squared plus 4, right? Same thing, we're just labeling this t instead of x. It would be a parabola shifted up 4 boxes. That is always greater than 0. And so that's -infinity to infinity. Likewise, no matter what number I put in here, if I put in -5 quantity squared makes +5 plus 4. So there's your greater than 0. There's no value I can put in here that will make that come out to a negative.